I wanted to do a quick video on exponentials and logs, particularly logs, because they seem to give a lot of students trouble. Now this is just a review. It's assuming that you've seen all this stuff at some point and just need a quick kind of refresher on solving maybe log equations and exponential equations. When I see log expressions, there's a couple ways of looking at them. Reading log expressions to, say, 64 equals, the first thing I'm going to concentrate on is just reading these and getting used to seeing log expressions and being able to just simplify them as they stand. So I got a couple examples here. Log base 4 of 2, log base, let's say 9 of 27, and we'll go with, we're off the page, log base 7 of 0 equals. Okay, so when I see a logarithm, I see an expression that asks a question. Base, and there's the argument. It says base to what power gives the argument, right? So if I write it real small up here, if I have like log base b of x, asks a question. It says b to what power gives x. Just like this says, if you read this notation, it means what number when multiplied it by itself gives x. This says b to what power gives x. So it's one way of asking a question. So therefore, when you see this, it's asking 2 to what power gives 64. So then you just think about it a little bit, and it's 6, because 2 to the 6th is 64. And basically that's how all these things go, according to me. If you see a log expression without the base written there, just log, it's assumed that the base is 10. So this is asking 10 to what power gives 1000. The answer is 3, because 10 cubed is 1000. And we can keep doing these. Log base 5 of 1, 5 to what power gives 1? So that's going to be 0, because 5 to the 0 is 1. 4 raised to what power gives 2? Since 2 is the square root of 4, that's equivalent to 4 to the 1/2 power gives 2. So the answer is 1/2. Log base 9 of 27, that's a tough one, because it's not a whole number power, but if you take, they're both powers of 3. So if you square root 9, you'll get 3, and then when you cube that, that'll give you 27. So the answer is actually 3/2. The half for the square rooting to get you down to 3, and then the 3 on top for the then cubing to give you 27 rather. And then we got this last one down here, log base 7 of 0, that asks the question 7 to what power gives 0, and there is no such number, so this is undefined. Alright, you cannot take the log of something that's not positive, actually, because there's a correspondence with all these log expressions. These all correspond with some exponential relationship, and you cannot, there is no solution to the equation 7 to the x equals 0. There's no such number that satisfies this. So therefore log base 7 of 0 is undefined. It's just like trying to divide by 0, same kind of thing. Okay, so now these are really just things that we can do, that we can put into our calculators and figure out. If they're not whole numbers, you still have to understand the concept of what's going on here. For example, if you were to see, say, log base 4 of, let's say, 30, all right, you would have to recognize this as the power that 4 would need to be raised to in order to give you 30. Alright, so the answer is going to be somewhere between 2 and 3, because 4 squared is 16, and 4 cubed is 128. 128. So it's going to be some number between, that's a 2, between 2 and 3. And pretty much we have to rely on our calculators to figure these things out at this point. But the important part is just understanding what it is that they mean. A primary use in logarithms is solving exponential equations. So for example, if you come across something like, let's say, 3 to the x plus 1 equals, I don't know, let's say 18, and we say solve for x. So what do? You just undo, you have to undo the operations until you get down to the exponential part of it. So you just subtract 1 from both sides, it gives you 3 to the x equals 17. And what do you do here? Well, what you do is you have to do the inverse operation of the exponentiation here. And the inverse operation of an exponential is a logarithm. So what you do is, in order to undo this 3 to the x, you have to hit it with the inverse operation. So you log both sides. Log both sides, base 3. The way to write that down, I'll go through it slow, is you do log base 3 of 3 to the x equals log base 3 of 17. And now what happens on this side is the logarithm and the exponential, they undo each other, and out pops just x by itself. And that'll make a little more sense if you read it the way that we've been reading the other logs. This says, listen carefully, 3 to what power gives 3 to the x? Okay, so it's like saying, if I draw it up here, it's like saying 3 to what power equals 3 to the x. So if you look at it that way, it's easy to see that the exponents have to be the same. 3 to what power gives 3 to the x? Well, the answer is obviously x, right? If we said 3 to the 7th equals 3 to the x, and you asked for x, the answer would be 7. So this combination here, they undo each other, and out pops just the argument x equals log base 3 of 17. And that's the answer. That's how I would accept the answer. So the solution to the equation is the power that you have to raise 3 to in order to get 17. And let's see how that would work out. Okay, just keep it in mind, log base 3 of 17 is the power you'd have to raise 3 to get 17 out. So if we substituted that back into here, you would have 3 to the x. 3 to that power would give you 17. Plus 1 gives you the 18, and it works out. So we use logarithms to undo exponential equations. Let me give you another example of that. They all pretty much go the exact same way. You could say 5 times, say, e to the 2x minus 1 equals, say, 29. Alright, so solve this equation. Again, you do the regular rules of algebra just to work your way to the exponential expression. So you would add 1 and get 30, and then you would divide that by 5 to get 6. So I'm going to forego writing out all the details of that. Just get e to the 2x equals 6. Now, a couple different ways of solving it from here, but we're going to go with the log way first. You have the exponential base e, so do the the natural log operation on both sides, and you have ln e to the 2x equals ln 6. And again, what happens on this side, you hit the exponential with its inverse operation. So this will say e to what power gives e to the 2x. So the answer, via the previous reasoning, is just going to give you 2x. What it does is it undoes the exponentiation part and just returns whatever is in the exponent. 2x equals ln 6. And then you just take this number, which we recognize as the power that you'd have to raise e to in order to get 6, and divide it by 2. X equals 1/2 ln 6. And that's not the only way to go through with it, but that is one way of looking at it. Alright, so that's what you get. That's what I would take as an answer. It's something that you can plug into your calculator. Let me just take it a different way, though, starting from here. When you go here, so add 1 and divide by 5. Okay, that'll get you here. We could use properties of exponents, and instead of going straight there, we could interpret this as e to the x, e to the x quantity squared. All right, equals 6. E to the x quantity squared, because right algebraically, the 2 times x, you would do the multiplication, get e to the 2x. So what we could do now is square root both sides, and you'd get e to the x equals plus minus the square root of 6. But we would have to discard the negative square root because no exponential is going to be negative, so we'd have to take the positive square root, so we'd get e to the x equals the regular square root of 6, and then we could undo the exponentiation with a logarithm. So you would log base e, natural log both sides, ln of e to the x equals ln of radical 6, and they undo each other, and you just get x equals the natural log of the square root of 6. And they look to be different answers, but they're not, because if you remember, there are properties of logs which can convert these types of expressions into these types of expressions, and I'm going to go over that right now. There were 4 properties of logs that we use in, on occasion, solving log equations, and or just simplifying log expressions and things like that. One of them is the alright, if you have the log of any base, the log of a product, log of xy, that's equivalent to log x plus log y. Alright, the log of a product is the sum of the logs. So this kind of gives us an algebraic tool, a way to break apart logarithmic expressions with products. That's one of them. Another one is the log of a quotient. Log of x divided by y is log x minus log y. Alright, the log of a quotient is the difference of logs. And another one is a log of, say, x to the y, the exponent one. Alright, exponents pull out through logarithmic expressions. Alright, so this is equivalent to, you can kind of take this out and write the y in the front, y log x. And this is what we did with this example here. Right, the radical 6 is like a 6 to the 1/2 power, and via the that rule, it can just be pulled out in front, and you get 1/2 ln 6. So we already utilized that. And the last one is the change of base formula. If you have log base b, now I just wrote 10, but these 3 rules apply to any log that you want. Log base b of x. Any log can be changed. The base can be changed. And that's why it's called the change of base formula, right? Log base b of x can be rewritten as log base anything you want of x divided by log of that same base of b. Now this is typically useful for calculator expressions. Most calculators only have log base 10 buttons or log base e buttons. So if you were to come across an expression such as say log base 9 of 100, and you needed to do that, what you could say is you would enter that into your calculator via the change of base by writing, you could either go with log base 10 or ln, the base doesn't matter, but you could say ln 100 divided by ln 9. And it's just something that you could use your calculator for. You could figure that out. But these are the 4 main properties here. In case you ever have to simplify log expressions, just to make sure everything has to be positive. All right. So if these products are positive, this has to be positive. The arguments have to be positive because you can't take a log of something that's not positive. So don't forget about these. These come up in solving equations. So I got a couple of log equations for us to solve. But another way of looking at these is the equivalence of logs, of log and exponential equations. When we have some of the other ones I did earlier, if we had, say, log base 2 of 64 equals 6, this is equivalent to, this logarithmic expression is equivalent to 2 to the 6th equals 64. So that if you're solving some kind of an equation, if you have something in here that you have to isolate in an equation, you could rewrite the log equation as an exponential. So for example, I could say log base 2 of what number equals, say, I don't know, we'll go with 100 again. And if this is an equation that you have to solve, you could just use the equivalence. You could rewrite this log expression as its equivalent in its equivalent exponential form, which means if you look, this is the base, so this is equivalent to 2 to the power of, the exponent is what's on the other side, 2 to the 100 equals x. So in this case, x is 2 to the 100 power. Okay, that's how you would isolate x. Let me just do another example of that. If you have like a full 1 minus log base 2 of, let's say, 7 minus x equals 3. And you want to solve this, you would work your way to the log expression by subtracting 1 and then flipping the sign. So that'll give you log base 2 of 7 minus x equals minus 2. Right? You take away the 1, then flip the sign. So what you have to do is turn this log expression into an exponential expression, thereby getting the argument out. So you refer back to what's up top here, and you notice that the base is going to stay the same. Right? So this is going to be equivalent to, let me just, if I write it with that same way here, okay, you'll get 2 to the power of what it, right, 2, this turned out to be 2 to the 100. So this is going to be 2 to the 100. 2 to the minus 2 is going to give you 7 minus x, like that. And then, so that's 1/4 equals 7 minus x. And then you would do algebra and just get the x equals 7 minus 1/4. Like that, and just work it out that way. But that's how to undo it whenever you come across a logarithm. You could, one way to do it is just rewrite it in exponential form. Come up with another one here. Let me see. We could have let's see, ln of radical x plus 8 equals 2, and we could say solve for x. So what you would do is, remember there's a phantom e here, you would rewrite this logarithm in exponential form to get to the inside. So the way that goes is we rewrite, it means that the base raised to this power gives you the argument on the inside, square root x plus 8. These are equivalent expressions. It's just that this one is more convenient for, it's just a thing that we can do to this in order to get at the variable that we need. So then from there you would just use the regular rules of algebra, just square both sides, and you get e to the 4th equals x plus 8. And then subtract 8 from both sides, and you get e to the 4th minus 8 equals x. You'd have to go back in and make sure to check it, but that one is going to work, right? You plug it in. So whenever you come up with a log expression, just rewrite it in exponential form. Another way of doing that, though, a different way that I like, is to exponentiate both sides. So if you have log base 2 of x equals 19, and you want to solve for x, instead of rewriting this in exponential form, which I'll just put over on the side here, that's, I write this, that's 2 to the 19th equals x. Another way to do this is to use inverses, just like we would for regular algebra. If we want to, if the addition operation is standing in our way to get to a variable, we hit both sides with subtraction. So in this case, just a different way of looking at it is to, you have the logarithmic operation on both sides here. So what you could do is hit both sides with its inverse, which is exponentiation. And what that entails is you make both sides the exponent of whatever this base is here. So you have this equals this, make them both exponents. So you'll say 2 to the power of log base 2 of x equals 2 to the power of 19. And now what this does, because they're inverse operations, 2 to the power of something and log base 2 of something, they're inverses. So they undo each other, and out just pops whatever the argument is. So you'll just get x equals 2 to the 19. And of course it's going to work out the same way. Just a different way of looking at it. I like that because it's consistent with operations. It's consistent with inverses. That's how we solve every algebraic equation. We always use inverses, so why not use inverses here? So when you see a log, you would just do the exponentiation operation on both sides, and that will give you the answer if you maybe forget that this relationship holds. Either one is fine. I do have one final one, though. One last logarithmic equation here, and that's log of 5x, right, plus log of x minus 1 equals 2. When students see this, they want to get rid of both logs at once, but that's not gonna work. You have to combine these first. You have to use the rules that we talked about earlier, the properties of logs, to condense this expression into a single logarithm first. So we have the sum of two logs, so we can rewrite that as the log of a product, the log of this times this. So these two are equivalent to log, and I'll just write the 10 down there to remind me, of 5x times x minus 1, which would be 5x squared minus 5x, and that equals 2. And then from here you have your choice of what to do. You could either exponentiate both sides with 10 and write 10 to the power of this whole side equals 10 squared, or you could just rewrite the equivalent in the exponential expression. You could rewrite the log as its equivalent exponential expression, whichever suits your fancy. I'll do it that second way, and I'll say 10 squared. This means that 10 squared equals 5x squared minus 5x, right? So we want to isolate this. The way that we do that, this is 10 squared is this. So this is how this works out, and that's 100 equals 5x squared minus 5x. And the hard work is done because from here it's just a regular algebraic equation. You would divide both sides by 5, so we get 20 equals x squared minus x. Bring over that 20. 0 is x squared minus x minus 20. And then it looks like this is going to factor, so you get x minus 5, x plus 4 equals 0. So we would get out of this either x is 5 or x is minus 4. So I write that, 5 and minus 4. And just make sure you go back and try to plug those numbers in to make sure that they work. The 5 looks like it's going to work, but the minus 4 is out because we don't want any negative numbers in there, so we managed to get an extraneous answer. But that's pretty much all there is. Properties of logs, simplifying log expressions, solving log equations, and solving exponential equations. That's pretty much all that you need. And so that'll be that.